Let's look at another cylindrical coordinates example. So part A is to convert a point 0, -4, 3 from Cartesian to cylindrical coordinates. Part B, we're going to transform this vector field, which has an x component and a z component, to cylindrical coordinates. And then finally part C, we are going to evaluate the vector field at that point in space. We're going to do that in Cartesian and cylindrical systems. Let's get started. So part A, convert t to cylindrical coordinates. Alright, so what you have to remember is that rho is going to be the square root of x squared plus y squared. So that would be 0 squared plus minus 4 squared. And so that just gives us 4. Right? And then phi is the inverse tangent of y over x. So that would be -4 over 0. Well, what is that? Is that undefined? It's actually well defined, believe it or not. Maybe not well, but it is defined. If you imagine here's x, here's y, you go -4 down y, right, and 0x, so that puts you here. So what angle is that? Right, that is 270 degrees, exactly 270 degrees. All right, so that's phi, and then remember z is z, so z equals 3. So we have our point now. It's 4, 270 degrees, 3. That's the answer to part A. Okay, B. So we're going to transform that vector into cylindrical coordinates. Now first, remember again that rho is the square root of x squared plus y squared. So I bring that up. Why? Well, we look at our vector field and we see lots of square roots of x squared plus y squared. Okay, so we're going to want to recall that. Now also what we need to recall, or what we need to memorize, or we need to check our notes or our textbook, is that the matrix, the vector transformation. So the rho component, the phi component, the z component is equal to, and then we have this transformation matrix. So we've got the cosine of phi. Okay, and there's no reason you have to memorize this really. Sine phi 0, then minus sine phi, cosine phi 0, and then 0, 0, 1, right? Because z goes untransformed. And then we're going to put into that our coordinates in rectangular form. So we have this is the x, this is the z. So let's look at the x, and that square root of x squared plus y squared, we know that is rho. So I'm going to call this rho, right, over, so, and then this thing is the square root of rho squared plus z squared, right? Because if rho is the square root of x squared plus y squared, rho squared is x squared plus y squared. So this is the square root of rho squared plus z squared. So that's the x component. There is no y component of our vector field. And then the z component is this minus y over, again, that same denominator. So y, remember that y is rho sine phi, right? So we're going to make this minus rho sine phi divided by that same denominator, rho squared plus z squared. Right, so that's what we've got. And then when we carry out the multiplication, we notice that q sub rho, right, when we do this multiplication, we get rho cosine phi over that denominator, square root of rho squared plus z squared. And then we have 0 times sine, and the rest is 0. And then when we carry out the multiplication for the phi component of q, we get minus rho sine phi over that denominator, rho squared plus z squared, right? And then when we carry out the multiplication, we get the z component of q, which remains unchanged, of course. Okay, over that same denominator. So this is what we have. So let's just be precise here. Our answer, our vector field in cylindrical coordinates now is rho. I'll just actually bring out the denominator, 1 over square root of rho squared plus z squared. I'll bring that out. I guess I could bring out a rho. Okay, and then what are we left with? We're left with cosine phi in the rho direction, right, minus sine phi in the phi direction, minus sine phi in the z direction, right? So that's what we have there. And that is our final answer for part B. Right. Okay, so now I'm going to just create some room. Feel free to pause the video if you need to. All right, but I'm going to delete some of that work, and I'm going to try to squeeze in C right over here to the right. Now, I want to evaluate Q at point T in Cartesian first. So let's just do Cartesian. So in Cartesian, my point is 0, -4, 3. So Q is equal to the square root of 0 squared plus -4 squared over the square root of 0 squared plus -4 squared plus 3 squared, right, in the x direction, minus, and then y is -4, so this becomes plus 4 over that same denominator, 0 squared. I'm going to try to squeeze it in here, -4 squared plus 3 squared in the z direction. Okay, so when I evaluate that, I get 4 in the numerator here, and then I have 16 and 9, 25. That's nice. The square root of that is 5. 4/5 in the x direction, and I get 4/5 in the z direction as well. Okay, so we evaluated the vector field in Cartesian coordinates, right, at that point. So now let's consider cylindrical coordinates. Cylindrical coordinates. All right, so I need to evaluate this thing in the box. So remember that rho is 4, okay, z is 3, and so I need cosine phi and I need sine phi. Now in this case, yeah, phi is 270 degrees. So you can think again of this picture here. And so what is the sine of that angle? The sine of that angle is -1, right? And the cosine of that angle is 0. The x and the y and the x components respectively. Okay, so now we plug this in and we get Q is equal to, again, rho is, we said 4. So this is 4 over the square root of 4 squared plus 3 squared. So that's 16 and 9 is 25. So that's the square root of 25, which is 5, times cosine of phi is 0. So 0 in the rho direction, minus sine phi. Sine phi is -1. So that makes that. Okay, and then we've got minus sine phi again, so that's plus. Okay, and that's our answer. So which one is correct, right? We've got it in Cartesian, we've got it in cylindrical. Well, first of all, they look very similar, but they're both the same thing. They're both telling you the same field. It's just that one's expressed with x, y, and z, and one's expressed with rho, phi, and z.